In the name of God, the compassionate, the merciful, Engineering Plasticity, Chapter 2, Stress Analysis, Part 3. In previous slides we talked about stress and we tried to give a precise definition for stress, and in this slide we are continuing with the components of stress but using tensor notation. Now for tensor notation, if you are not familiar with this kind of notation, I will put a video explaining tensor notations. Okay, as we discovered, stress has many components. As you can see here, we have 3 axes, and each of these axes are named 1, 2, and 3. Therefore, this is the plane of 2, 3. Okay, in the plane of 2, 3, we have 3 components of stresses. 2 of them are in the plane, sigma 1, 3 and sigma 1, 2. As we explained before, this one is due to the fact that we have this perpendicular to this plane is in the direction of 1, therefore we say sigma 1, and 3 is due to the fact that it is in the direction of 3, therefore that's sigma 1, 3, sigma 1, 2 again, and sigma 1, 1 is perpendicular in the plane. Okay, so these 2 are in the plane, this is perpendicular at it. And similarly we have plane 1, 3, and we have 2 components of shear stresses, sigma 2, 1, sigma 2, 3, and 1 component of normal stress. And lastly we have plane 1, 2, and we have 2 components, sigma 3, 1, sigma 3, 2 in the plane, and sigma 3, 3 perpendicular to the plane. Therefore, as you can see, we have 9 components of stress. Sigma ij is a tensor notation. I gets 3 value, and also j gets 3 values. We will put I equal to 1 to 3 and j equal 1 to 3. Therefore, we have sigma 1, 1, sigma 2, 2, sigma 3, 3, sigma 1, 2, sigma 2, 1, sigma 1, 3, sigma 3, 1, sigma 2, 3, sigma 3, 2. They change alternatively. Okay, so we get 9 components with this notation. So this is very simple and useful notation which we use in our relationships and calculations and computations. So this sigma ij can be shown as a matrix with 3 columns and 3 rows. In general, we have this tensor notation A, I, J. As you can see, I can be allocated values of 1 to m, and j is allocated values of 1 to n, 1 to n. Therefore, I is the number of rows and j is the number of columns. Therefore, we say that this is a matrix of m times n. That is in general. Obviously, m and n can be any values, and we show this tensor notation is a very brief and very suitable notation. Let's see what the tensor stress tensor is. Well, we showed before that the traction vector or the force intensity or the stress. Force intensity, what does it mean? It means that how intense the force is on an area. Okay, so that's a stress. And we showed before that Tn is equal to limit delta F, delta A tend to 0. Okay, so this is the definition of traction force, traction vector, and also stress. We talked about it earlier. Now, a state of stress at any point also we can define it like that in different direction. For instance, the Tex is in the x direction, x is perpendicular to this plane, so we get this. Tey in that plane, and we get that. And Tez also. So here we have shown the vector notation, and in previous slide we showed the tensor notation. Okay, we will use these kind of notations depending which one is more suitable for our purposes. And stress at a point can be shown like that. We show an infinitesimal point with a cube. Okay, so as you can see, this cube has many faces, in fact 6 faces, and on each face or on each plane like that we can show the components of the stresses. Obviously we have only 9 components, but some of these components are negative and positive in different directions. For instance, that's in the z direction is positive, this one is negative, and so on. So that's why we have many components here, but in fact there are only 9 of them. Okay, as shown here. And also, so we can say that sigma x, sigma xy, sigma xz, but this sigma xy and sigma xz usually we show it with tau, because tau represents the shear stress. So as you can see, the diagonal of the matrix shows the normal stresses, and the other components of this matrix are shear stresses. Now this is our cubic element, and these are the stress components on the faces of the cubic element. And here we want to write down the equations of equilibrium, okay, because this cubic element is under the action of the stresses, and it is at equilibrium. Therefore we can write the equations of equilibrium. Now, to write the equation of equilibrium, we could take moments about x-axis, y-axis, and z-axis. We could also write down the sum of the forces in different directions and put them equal to 0, and to see what we get. Therefore, we start from the z-axis. Taking moment about the z-axis, we can, for instance, for this face of the cube, sigma zz is perpendicular, is parallel to z, has no moments. So only sigma zy and sigma zx have moments. Now here obviously moments is to do with forces. Therefore we must multiply sigma by the area to get the moment. Okay, so for instance, sigma zy in here, sigma zy multiplied by this area, and this area has delta x and delta y. So delta x times delta y is the area of this plane, times sigma zy is the force, and times this distance. This distance, it is in the middle of this plane, so the distance is delta x over 2. Therefore the moment is sigma zy times delta x times delta y times delta x over 2. And because the moment is anti-clockwise, usually we take the anticlockwise as positive. Therefore, this is positive moment. And the other one, sigma zx here, again times the area of the plane, which is times delta x delta y, and because it's in the middle of the plane and the distance to the z is that much, we go half of this, which is delta y over 2. Therefore, the moment is sigma zx times delta x times delta y times delta y over 2, and the sign is negative because it is clockwise moment. Okay, we take anticlockwise as positive and clockwise as negative. Similarly, we could have moments for all of these faces, all of the stresses in all of the faces, except that sigma zz has no moment about the z-axis. We could also take moments about x and y-axis, and if we do that, many of these terms will cancel out, and we will end up with this. Okay, sigma. We will end up with three equations like that: sigma xy equal to sigma yx, sigma yz equal to sigma zy, and sigma xz is equal to sigma zx, simply by taking moments. And what does this mean? It means that our stresses are reduced from 9 components to 6 components. So we have 6 components of stresses because these are all equal. In order to have equilibrium, we have to have these to be equal to each other. And we are going to further develop this discussion on the stress, and here we are going to see what are the components of stress on an arbitrary plane. This is an arbitrary plane and this is the stress. We want to know what are the components. As we talked about it before, we said that in a body which is under the action of stresses or traction forces, we can have different planes. We could consider different planes at only one point, and depending on the angle of these planes, we get different states of stresses. Now here we want to find out a general equation, because here we have said that on arbitrary plane it means that any plane, okay, a general plane, a generic plane. Therefore, if we find the equations for an arbitrary plane with an arbitrary angle, then it is just enough to change the angle and we get the stress on any point and any plane. So that's what we are going to do. Now, if this S is the stress, then the components of a stress on an arbitrary plane are like that. Sigma yy, the configuration that I have put here, obviously sigma yy is the normal to this plane, and tau y is the tangential or shear stress component. Obviously this yellow plane, y plane cross section, is perpendicular to the y axis. That's why we got this sigma yy perpendicular to the yellow plane. Okay, but this is an arbitrary plane because we could get any arbitrary plane and we could have our axis any way we like. Then what we will do is that on the plane, on this plane, which is perpendicular to the y direction, and we have this shear stress tau y. We have written tau y because tau y is perpendicular to y. we could write down the component of this tau y in the direction of x and in the direction of z. Therefore, as I have shown here, that is the component of tau y in the direction of z, and that is the direction of tau y in the direction of x. So what we have done, we have this general stress on an arbitrary plane, and we have taken this as its components, sigma y, sigma, and tau y, and this tau y has components on the plane, on the yellow plane or y plane, and the components are in the direction of z and x as we have resolved them. In order to further develop this state of stress, we take a very general plane, in the cube, because in this cube we showed that we have on each face of the cube we have three components of stress, and we want to translate these components into an arbitrary plane. So we should take an arbitrary plane in the cube. How do we take the arbitrary plane in the cube? We take a doubly oblique plane. What does it mean, doubly oblique plane? Oblique means it has an angle to these lines. So if you see this plane, which I have shown here as a triangle, but in fact it is an infinite plane. It is continuous in all directions, but it is easier to show it as a triangle. It has it makes angles with x, y, and z directions, and these angles can change. So if we change these angles, the plane changes, and we could have infinite planes. That's what we want, because we said that we want an arbitrary plane, a general plane. And if we find the stresses on a general plane, then we have the stress on any plane. So this is a general plane because it makes angles with different directions, and these angles are arbitrary, and we can change them any way we like. So that's why we call it a doubly oblique plane, because it has double gradients. Now, again here I will do what we've done in the previous slide, which is take an arbitrary stress on this arbitrary plane as S. Okay, what is this N? This N is perpendicular to this plane. This plane we call it ABC, and N is the perpendicular normal vector to this plane. The normal, how do we draw that? We start from the origin and make a perpendicular line to this ABC plane and continue it like that. So that's N, the perpendicular vector to this plane, and we know that we have from previous explanations that any plane is just shown by its normal. So this normal in fact is showing what plane we mean. Okay, so if we find the angles of these normals with x, y, z, then the plane is known and determined. And so this S is a general state of stress on this plane. Right, now we can have the component of stress on each phase of this element, because our element was previously a cube. Okay, so this OCB is the same as that cube, faces of the cube. This is one face of the cube, the other face of the cube, the other face of the cube. So this component, we had it before on the face of the cube, so we put it here. Sigma xx, tau yx, tau zx. I just want to show you. See, these are the faces of the cube. Now I have drawn this triangle in here. So on this face of the triangle I have these components. On this face of triangle I have that, and on that face I have this. So that's why I have put here these components. These are the components that we showed on the cube. Okay, and this is a general state of stress. I want to relate this together. And similarly, we have these components. You can compare this to that cube, and you will see that these are the same components that we show on the cube, because these surfaces or planes are the same as those faces of the cube. Okay then, so that's what we have. That's the state of the stress generally, and this is an arbitrary state of stress, and this is the normal to the plane ABC.